Okay, so we're starting it. Originally, this was going to be Unit 6, but I decided that I liked this better, so I'm going to make it actually Unit 5, and we're going to do Unit 5 when we come back, because I thought this was more fun for before Christmas break, so I kind of flipped them. So all this is going to say Unit 6, but it's actually Unit 5 for you guys. So basically what we're going to do in this unit is we are going to revisit atomic structure, and we're then going to talk about periodicity, which is basically periodic table and the trends on the periodic table and how they repeat and all of that stuff, which we again have had an intro to, but like I said, a lot of this you're going to have seen before, but we're going to take it one step further. So we're going to do a little bit of review today, but then you're going to learn an additional equation, and we're actually going to talk about waves, and you guys are going to learn how to predict what they're going to do. Okay, so first off, let's do a little bit of review. Let's talk about electromagnetic waves. So let's talk about light. Light is what is made up of electromagnetic radiation. So when you see light coming in, you're actually seeing a type of radiation. You are seeing electromagnetic waves. Electromagnetic radiation consists of both electric and magnetic fields at right angles to each other. So when you see something, you're actually seeing a combination of two or more things. So this is what a nice pretty picture is. And as you can see, as the waves move, they always go to the same peak as the wave. You guys, it's kind of like you take a string and two people hold the string and you go like this. Technically, it continues to go even after you stop putting the motion through. And in a perfect world, every single wave would hit the same height and the same bottom, and it would just continue to go. We don't live in a perfect world, so that's not actually what happens. But in a perfect world, waves should continue to go in the same spot, and the wavelength between each wave, as you see in this picture, should be staying the same. For one wave, the wavelength between it should always be the same. So let's review the parts of a wavelength. I don't think there is an actual picture on but if I was you, I would draw it off to the side. Okay, so here we have a picture of a wavelength. Sorry, my computer's being silly. There we go. Okay, so here we have a picture of a wave. So let's draw a line right through here. This is representing 0. So this is like where the wave started. So again, if you and your partner are holding a piece of string and you pull it tight, this would be 0. As you go up and down, it goes below and above 0. But let's right through the middle is going to be 0. And so up at the top, we have something called our crest. That's the highest possible. Down here at the bottom, we have something called the trough. This is as low as it goes. And again, in a perfect world, the wave should hit the crest and the trough at the same point every single time. And the between crest and crest, we have something called our wavelength. So how much distance is between crest and crest? And this is, we're going to be talking about it a lot. The bigger the wavelength, the safer the wave. So like radio waves are very, very, very long. Because right now you guys are being bombarded with radio waves and it's not hurting you. So they're very, very, very long, so those are safe, which means there's a lot of distance between crest and crest. This is why radio waves can travel so far. Okay. X-rays, not as safe, right? That's why you don't want to go get an X-ray every day. That's why X-ray technicians stand behind the wall or they wear the lead vest, so on and so forth, so that they're not exposed, because those are much shorter wavelengths, which means they are more dangerous, and that's why they don't travel as far. Okay. Another thing is this distance right here, which actually isn't here, but the distance between the top of your crest to the 0 point, this is called amplitude, which we're going to be talking about here in just a minute. So on your notes, there are 3 main parts of a wave. We have wavelength, and we have something called frequency, which I'm going to talk about in just a minute, and then we have the amplitude. So I talked about wavelength, I've talked about amplitude, so now I'm going to spend a little bit of time talking about frequency, okay? Okay, so I kind of already started talking about it. I talked about wavelength, and the distance between each wavelength means that it's really, really long, and those mean that they're safer, right? So if the distance between 2 crests is a great number, is a big distance, how many waves are you going to be bombarded with? Not very many. You're going to be bombarded with less. So this brings in the whole idea of frequency. Frequency is the number of cycles in 1 second. So this is your frequency. And that is really hard to read. I should change my color. Let's do red. There we go. Frequency. Okay. Frequency is measured in hertz. Okay. Hertz is actually kind of a weird unit. Its shorthand is Hz, but what a hertz is, if we actually look at the definition of frequency, frequency is the number of cycles in 1 second. So if you're trying to write, is it going to be on the top or the bottom of the denominator, or on the fraction line? Is it going to be a numerator or denominator? A second. How many cycles you have in 1 second? Just think. The second's going to be in the bottom, just like we do meters per second, right? Miles per hour. So if we're talking about how many cycles you have in 1 second, we're talking about cycles per second. So actually, the second goes on the bottom. So another way to write hertz is to write 1 over s. And honestly, you need to be able to go back and forth in your mind between hertz and 1 over s, because when we're doing our problems here in a minute, when we're using the equations, you need to be able to remember that, oh, hertz is 1 over s, which is going to make my seconds cancel out. So you need to be able to go back and forth between the two. All right, so let's look at a picture of our waves. In this picture, we have I and II and III, and we have 3 different types of waves, correct? So let's just, before we do any math, let's just think logically about these. Which wave has the highest frequency? The second one, II, right? It has the highest frequency because you can see lots and lots and lots and lots of waves, right? Which one has the lowest frequency? The third one, right? I. The third wave. And then the first one's kind of in the middle, correct? So, high frequency, how does that relate to wavelength? If you have a really high frequency, you have a short wavelength. So remember how we've talked about this several times. We've talked about inversely proportional and directly proportional. So what do you think wavelength and frequency are? They're inversely proportional, which means as our wavelength, which is this fun symbol right here, wavelength goes up, our frequency should go down, correct? And so the opposite happens. If our wavelength goes down, then our frequency should go up. And so while we're on the slide and we're starting to see a little bit of Greek symbols, correct? Again, we've seen these Greek symbols before, but let's talk about them for just a second. So let me put my whiteboard up. All right, so I just put, in order to solve for frequency wavelength, we are going to have an equation that looks like C equals wavelength times frequency. And we get a constant and we get 2 Greek symbols. So the first Greek symbol, which is right here, this is your wavelength, this is called lambda. To write this, what I always do is I draw this part of the symbol first. I draw this part of the symbol first, and to me, it looks like a wave. Doesn't it look like a wave if you just look at that part? So I just kind of draw it at a diagonal. Doesn't that look like a wave? And then I just add a little tail. And this is the symbol for your wavelength. And then this symbol over here is the symbol for frequency, and it looks like a V, doesn't it? But it's not a V. Okay, and it's very, very important that you denote the difference between this and a V, because in the new equation you're going to learn today, we have velocity in it. So you need to make sure that you are doing a good job of writing frequency with a tail. See how it has like a tail? Because in a second we're going to be talking about velocity, which doesn't have a tail. Okay, so this is frequency. And this is going to be velocity here in just a second. Okay, wavelength. What do you think the unit is for wavelength? Length. Meters. Length is usually a measure of distance, right? So this is going to be meters. What's our unit for frequency? We just talked about it. Hertz, which is the same as 1 over s. And then does anybody remember what our units are from velocity from physical science? Just meters per second. That's acceleration. Just meters per second. Okay. All right, so really quick while we're still talking about this, I also want to talk about C, because again, we've been taught this, but it's been a while since chemistry, right? So C is actually the speed of light. And the speed of light is 2.998 times 10 to the 8th meters per second. Well, this actually, you can see the speed of light on the next little section. You see it? Okay, and we're actually, for today and for these calculations, I'm going to let you guys round that just so it's easier to put in your calculator. It's not going to affect our calculations that much, but we're going to round this to 3 times 10 to the 8th just to make our lives a little bit easier when we're putting stuff in the calculator. Okay? All right, so let's continue with our notes now.
Wait, can you say it again when wavelength increases?
And when your wavelength increases, your frequency decreases, and vice versa. Okay, there are a lot, wow, weird symbols. There are a lot of types of EM waves, electromagnetic waves. Typing out electromagnetic 50,000 times. It's a little old, so I shorthanded it as EM. So when there are lots and lots of types of electromagnetic waves, and each one has a different wavelength and a different frequency. So in place of these weird symbols, for some reason, probably because I had my Greek letters in there, it did not show up on the screen correctly. So in place of these crazy, we're going to have wavelength and we're going to have frequency. All right, which brings us to the electromagnetic spectrum. We've seen this before, correct? Okay, so just to kind of refresh our memory, if we look at this, it puts in order the dangerous waves, the safe waves, right? So over here we have our radio waves. Radio waves have a very long wavelength, very short frequency, right? So they're pretty safe. They're not going to hurt you, right? That's why radio waves, you're bombarded. I mean, right now, as you're sitting in your chair, you're being hit with radio waves, and it's not hurting you. Okay. Over here, however, the most dangerous ones are gamma rays, which, if you remember talking about nuclear radiation in chemistry, we're talking about gamma rays. Those are very, very, very dangerous. And in between, we have a scale, and you can see the low frequency. You can see the visual long wavelength, low frequency, high frequency. You can kind of see but then this little tiny portion of the electromagnetic spectrum is the visible. So this is the only part of the electromagnetic waves we can actually see with our eyes. And remember the whole Roy G. Biv. And again, I'm not going to make you memorize this. Back there on my periodic tables, my classroom set, I actually printed off color copies of this that you guys are more than welcome to use on your test. So you don't have to memorize why memorize when you can use it as a resource, right? Okay, you can't really see because of the picture, but on your next bullet on your notes, it says blank is the only part of our eyes can detect. What is the only part of our electromagnetic spectrum that our eyes can detect? The visible, correct? All right, so let's talk about the speed of light. Okay, the speed of light is what variable? C. And in a vacuum, if you remember back to physical science, this is when you can take out friction, you can take out gravity, you can take out all these things that makes waves not perfect, right? So in a vacuum, the speed of light is 2.998 times 10 to the negative, or not negative, times 10 to the 8th. And meters per second. But again, like I said, for these calculations, we're going to make our lives a little bit easier, and we're going to use 3 times 10 to the 8 meters per second. That 1/1000th of a place is not going to affect our calculations that much. Okay. All right, so here we see the equation again for the speed of light, and let's do an example.
May I have your attention, please? Wrestling chanters need to report to the gym at this time. The chanters need to report to the gym.
All right, so let's do an example. So it says, what is the wavelength of light with a frequency of 5.89 times 10 to the fifth? So we're going to use this equation, but we're going to rearrange it, right? Because we don't want to solve for C, we need to solve for the lambda, the upside down looking Y or the funny looking H, right? So if we rearrange, we have to divide each side by our frequency, right? So our wavelength is going to equal C divided by our frequency, right? So our C is 3 times 10 to the 8th meters per second. We're going to divide that by our frequency, which is 5.89 times 10 to the 5th hertz, which is the same as 1 over S. So now we can see our S's are going to cancel out, right? So if we put this in our calculator, how many significant figures do I get to keep? 3. And so we are going to get an answer of 509 times 10 to the negative second meters. But we all know a little bit about scientific notation. It's going, basically, this isn't correct scientific notation, so we need to move the decimal. So if we move the decimal twice, it's going to take away this, and we're going to get 5.09 meters. I think I just put in my calculator wrong. So basically, I have an eraser option. We didn't have to do any of that. It was just 509 meters right up from the beginning. Sorry, I guess I pushed something wrong in my calculator. All right, so let's do another example. This example says, what is the frequency of blue light with a wavelength of 484 nanometers? So first of all, nanometers, we can't be in nanometers, we have to be in meters. And secondly, we're no longer solving for wavelength, we're solving for frequency. So C is equal to our wavelength times our frequency. So we need to solve for frequency this time around, correct? So frequency is going to be equal to C divided by wavelength, correct? Our C is our speed of light, which is 3 times 10 to the 8th meters per second. But in order to get that meters to cancel out, we have to convert our nanometers into meters, which is a really, really, really easy fix. Okay, over there on the side of the wall, which I know it's kind of small, but I have written the prefixes, and over to the side I have written their scientific notation. So nanometer, if you look next to nanometer, you see times 10 to the negative 9th. So to convert it to meters is really, really easy. We just write 484, we add the times 10 to the negative 9th, and now it's in meters. So then we just have to plug this into our calculator, and hopefully I did this one right too. But we are going to get 6.19 times 10 to the 14th, and what's my unit going to be? 1 over S, which is hertz. So is this a pretty high frequency? I mean, think, add a whole bunch of zeros after that. So is this going to be a safe wave or a not so safe wave? Not so safe wave. We could go look it up on the electromagnetic spectrum, but we'll do that here in a minute. Okay? All right, so let's keep talking. Let's keep talking about waves. All right, in 1900, we had some discoveries, and we discovered that matter and energy were seen as different things from each other in fundamental ways. So matter and energy are not quite the same thing. They involve each other, but they're not the same thing. So we discovered that matter was made up of particles, which we later named atoms. So matter is made up of particles called atoms. However, the energy could come in waves. So basically, we came up with the idea that particles are not necessarily always waves. Sometimes they are, Sometimes they're not. Sometimes they can be both, but they can be different too. Okay. Max Planck, which was the scientist who kind of started coming up with this idea, he found that as we cooled hot objects, we could not explain how their energy worked, and we could not put it in terms of a wave. When cooling objects, they release heat waves, right? We were no longer could see this. And he actually, which I talked about this a little bit in chemistry, but basically Max Planck was the one who came up with the photoelectric effect. And basically what he did is he studied, and I'll draw a picture, you guys don't have to. But basically, he had a thin sheet of metal down here. And basically what he did is he studied the reflection of light off of a sheet of metal. And basically what happened was electrons would kind of come off, and based on the number and how fast electrons came off, he could figure out the amplitude of waves. And so he is the one who came up with the photoelectric effect, and we're not really dealing with that right now. But that was his main discovery, and that is how he came up with the idea of particles and waves, so on and so forth, okay? But he came up with the idea of energy, and he said that energy is quantized. Planck found that your energy came in chunks with a predictable magnitude. So he found that our energy is equal to N. What's N again? Usually dealing with moles, it's a whole number integer that we usually get from a balanced equation, right? He found that energy is equal to N times H, which is his constant that we'll talk about in just a second, times our frequency. Okay, so H is called Planck's constant, and we can see it here. H is equal to 6.626 times 10 to the negative fourth joules per second. No, I'm not going to make you memorize this. Yes, it'll be on your test. It is constant, just like last time I gave you the rate and I gave you the specific heat of water. Okay, this is a constant. However, probably after today, after we use this number 3 or 4 times, you're going to have it memorized because it's pretty easy. 6.626, there's a lot of repeating sixes, right? So you're probably going to have it memorized, but no, you do not have to have it memorized. But basically, Planck came up with the idea of these packets of HV. So if we take our frequency and we times it by this constant, we are going to get packets of something called quanta. Do you guys remember me talking about that in physical science? And it being one of those concepts that was really, really hard for us to understand. Okay, quanta is a plural form of quantum. And if you guys remember, quantum is the amount of energy it takes to move an electron. So remember in chemistry when we talked about electrons jumping between energy levels, and the only way that they can jump between energy levels was for them to absorb a certain amount of energy, usually in light, not always in light, but usually in light, and the amount of energy it takes to jump between the first and second energy level can be termed a quantum. So if we have lots of quantums, we call them quanta. So quanta is the amount of energy it takes to move an electron. It all kind of starting to come back to us a little bit. Okay, so more specifically, we're actually talking about, because I said usually it's the form of light, correct? So let's talk about light a little bit. So Einstein is the one who actually came up with the idea of light quanta, which we actually give a different term. So electromagnetic radiation is quantized in particles called, does anybody remember what light quanta is called? Photons. So photons are quanta light. So when we are talking about a specific amount of energy needed to move electrons between energy levels, and we are specifically talking about light energy, we term it a photon. So photon is light quanta. I haven't lost anyone yet, because this is where, in chemistry, this is where I lose everybody. So the second go around, we're good? Alrighty, awesome. Okay, each photon has a specific amount of measurable energy. Every single photon, which is why we can tell how many energy levels elements have, how many energy levels atoms have, because we can study the light that they give off. based on the amount of light and the type of light given off, we can figure out how much energy is being absorbed and released. Okay, so this gives us, basically, he took Planck's equation and he just took out the n. So he said we can find energy by taking h, which is Planck's constant, and timesing it by our frequency. Since there is a given, since every energy level releases the same amount, it really doesn't matter. N is the amount, right? It doesn't really matter because every electron does the same thing. So we can just throw that out and make our lives a little bit easier, make our calculations a little bit easier, and we can just set energy equal to h times frequency. Okay. However, let's do a little bit of work. Einstein is famous for his equation E equals mc squared, and we all have this memorized even though we probably never actually dealt with it before because we've seen it on TV, so on and so forth. So basically, we know energy. We know energy is equal to h frequency, right? We also know energy is equal to mc squared. So if we combine these two equations, we should be able to come up with an equation to give us the mass of a photon, because this m right here is matter, the mass, correct? So if we combine these two, we should be able to get an equation for mass, and I'm just going to save you guys a little bit of work, and I'm just going to tell you what it is. Mass is equal to h divided by c and our wavelength. So basically, if we combine our energy equation and we combine our c equals wavelength times frequency, and then we use it with energy equals mc squared, and we do a whole bunch of substitutions and canceling out, we will get an equation that allows us to solve for the mass of any given photon. And what's a photon again? A quantum of light. So we're talking about a specific amount of light energy, correct? Alrighty. So, which is it? Is energy a wave, like light, or is it a particle? Well, what do you guys think?
Both.
Energy can be both. Energy can be a wave or a particle. Okay, this leads us to a theory called, it leads us to a theory with a fun name, and it's called the wave particle duality, which basically means waves can act like light or waves can act like particles. Particles are, you want to remember from 2 seconds ago? Atoms. So waves can act like particles, or energy can act like waves, or energy can act like particles or atoms. Okay, they can act two ways, which are honestly quite the same. So what about the other way? Is matter a wave? Yes. So they can go back and forth. All right, so how do we know about these wave particles? Well, basically, we can see the evidence. So when light passes through or reflects off a series of thinly spaced lines, it creates a rainbow effect. So this is how we can see light. We can see rainbow. We can see the reflection. It's going through a prism, so on and so forth, right? So we can see that light, so that's not so hard. However, what happens to we saw the whole spectrum. The visible part of the spectrum was very, very, very tiny, correct? So we can see that part, so that's easy for us to study. So how in the world do we study the waves we can't see, right? So basically we can't see those waves, but we can see how they interfere with each other, because we've all seen, if you throw a couple of rocks into a pond, if you throw one rock, it makes a nice pretty wave going out, right? But if you throw two or three, what happens when they start to interfere? They kind of crash and they start to combine and they change the wave a little bit, correct? So basically, to study other waves, we have to see what happens. So visible light, or if we have one hole, the waves go through the holes and it makes one curve, just like we throw one rock into the lake, and we're not really going to be able to study it very much. So let's take two holes. So now it's like we're throwing two rocks into the pond. If we throw two rocks into the pond, we're going to get two waves coming out, correct? So if we have the particles going through two holes, we're going to get two waves, and as the waves go out, they get bigger and bigger and bigger, right? So basically, when you throw two rocks into the pond, as it goes out, the waves get bigger and bigger and bigger and bigger, right? Same thing's happening here. If we put two particles through these slits, the waves are going to continue to travel and they're going to get bigger. Right now, are they interfering? No, but as they get bigger, they start to interfere, correct? This part where they interfere, the crest will actually add together and make the waves bigger. And so then when they hit again, they're going to interfere again. Just like when you throw rocks into a pond, when the waves hit, they try to coexist at the same time, and the wave will change, but the waves are still there. Okay, so the crest will add together. So if we send several waves through there, we send 4 waves through there, at first they're not going to interfere, but as they start to interfere, we're going to get a whole bunch of interference going on, and we're going to be able to study that interference. We're going to be able to see that interference somehow. All right, so basically, when we're trying to study the waves that we can't see, we don't study the actual wave, we study the interference between the waves. And that's how we know how the other waves behave. So what will an electron do? All right, electrons have mass and volume, so therefore they are matter. A particle can only go through, how many slits do you think one particle can go through? One. Particle can only go through one slit. However, a wave can go through, in the example I just gave you, it can go through both slits, correct? So, do we ever really just have one electron? No. Most of the time we have multiple electrons. So when we're studying electrons, are we going to be studying one lonely wave, or are we going to be studying several? Several. So it'll honestly go through both slits as well, because very rarely are we going to be studying one electron. No. However, we can study one electron. So if we take an electron individually, what do you think it's going to behave like? Is it going to behave like a particle, or is it going to behave like a wave? It's going to behave like a particle. But most often, are we going to be studying an electron individually? No. Most often, we're going to be studying electrons as a whole, so therefore they are going to act like a wave, and we're going to be able to study them like a wave. So to kind of give you guys a visual of what I'm talking about, because the whole one slit, two slit thing is hard to understand, right? Let's look at a picture. So, if we're studying 1, 2 electrons, and it's hard to see in this picture, but we have several dots here, right? We can see several dots. So basically, in this, we're studying a particle. Do you guys see a wave? No, because there's not interference to study. If we're only studying 1, 2 electrons, are we going to get an interference? No, so we're not going to be able to see anything. However, as we throw more in there, they're a little bit easier to see, right? They're starting to interfere with each other. We throw a little bit more in there, they're really interfering with each other. And if we're studying a lot of electrons, what do we notice in this fourth picture? We can see a wave, can't we? So when we're studying lots of electrons, they behave like a wave because of all of how they interfere with each other. If we're studying one electron, that's a little bit more difficult. But if we study a bunch of electrons and we can study their interference, we can treat them like a wave. All right, so here comes a new equation that I said was coming. All right, so using the velocity instead of the wavelength, we can describe the speed of the wave. We get a new equation, and de Broglie was a scientist who came up with this equation. He said that if we know the wavelength, we can compare it to Planck's constant and momentum. Does everybody remember what momentum is from physical science? Your ability to move. So like, if you remember from physical science, objects with a really, really, really big mass have a lot of momentum, like semi-trucks. This is why in a car wreck, semi-trucks are a bad thing to be going because they have so much momentum because their mass is so big. It takes them a long, long, long time to stop. So that's what momentum is. If you have a small mass, like a bug hitting your windshield, it stops pretty quickly and goes splat, correct? Because it has such little mass, it has a little momentum. Well, momentum is equal to mass times velocity. So basically, de Broglie took Planck's constant and compared it to momentum and said that they are inversely proportional. So, based on this, we can calculate the wavelength of an object. Larger matter have wavelengths that are too short. So therefore, honestly, if you have a giant piece of matter, it's going to be really hard for us to study its wavelength because of the idea of momentum. it's going to have such great momentum. It's going to be hard for us to figure out its wavelength. So let's do some examples. You guys ready for some examples? All right. So the laser light of a CD is 7.8 times 10 to the second meters. What is the frequency of this light? So we are solving for frequency. So what equation do you think we need to use? C equals frequency times wavelength, because we have wavelength. We C is a constant, so let's solve for frequency. So frequency is C divided by wavelength. 3-variable equation, easy peasy for us. We're going to do 3 times 10 to the 8th meters per second divided by our wavelength, which is given to us as 7.8 times 10 to the second meters. Plug that into your calculator, and we're going to get 384 blah 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 thousand. And we're going to have to round, right? Because how many significant figures do we have? 3. So whatever, it's going to give you 6 figures, and we have to round to only 3, so we're going to round that number to 385,000. And what's my unit going to be? Hertz. That's not so bad, correct? That was an easy 3-variable one, but we're going to continue, because if you look on your notes, we have A, B, C, and D, correct? All right, so let's look at B now. B says, well, now that you know the frequency, let's solve for the energy of a photon of this light. So let's think about this. We had several equations for energy, right? We know the wavelength, we now know the frequency. What equation should we use to solve for energy? So we need to use energy is equal to H times our frequency. We just solved for frequency, correct? So again, 3-variable equation, plug in your numbers. H is a constant. It is equal to 6.626 times 10 to the negative 34th. And our unit for H was joules times seconds. Then we plug in our frequency, which we just found to be 385,000 hertz. Our seconds are going to cancel out, right? What are we going to be left with? Joules. So if you put all of these numbers in your calculator, how many significant figures do I get to keep again? 3, because we're given one number in our problem. So we're going to round to keep 2.55 times 10 to the negative 28 joules. Small amount of energy, right? Why do you think it's such a small amount of energy? It's a particle. It's a photon. Tiny, tiny, tiny. We're talking about an electron, right? All right, so now let's move on to C. All right, C says, what is the apparent mass of a photon of this light? So we know wavelength, we know frequency, we now know energy. What equation should we use to solve for mass? Oops. M equals H divided by C wavelength. Okay, H, 6.626 times 10 to the negative 34th joules times seconds. C was 3 times 10 to the 8th meters per second. Our wavelength was given to us in the problem, and it was 7.8 times 10 to the second meters. Hold on just a second. Everything is going to cancel out except for what? What unit are we going to be left with? So we need to remember what joules is. Joules is a kilogram times m per second squared. So our meters are going to cancel out, our seconds are going to cancel out. So what unit are we left with? Kilograms. So mass has to be in kilograms. The answer for this one is going to be 2.83 times 10 to the negative 45. And as homework, I want you guys to do I want you to finish D, and I want you to do example number 4 as homework, okay?